Let's discuss oscillation. This is engineering physics. In order for us to approach oscillation or oscillatory motion, we need to understand the principle of periodic motion. As stated, periodic motion repeats itself after a fixed interval. Fixed interval is a definite time frame, which we are more familiar with calling it a period. For example, the Earth is rotating around the Sun in a periodic motion. Suppose we get a certain point at its orbit. We know that the Earth will take 365 days to reach the same point. Similarly, for a child on the swing, it will take the same period for the swing to pass by a certain point. Oscillation or oscillatory motion is one type of periodic motion where the particle involved moves to and fro about a mean position. Mean position is the location where the particle is at equilibrium. At the time that a force is applied, the particle can move to a direction but returns to the mean position before it moves on to the different direction and at a certain amplitude gets back to the mean position. If the movement or oscillation is quick, we call it vibration. So oscillation and vibration have the same connotation. There are only two conditions to satisfy oscillation. One is that the period of a particle consumes to move to one direction from the mean position is fixed. Another condition is the particle should move at two opposite directions. With only these conditions, velocity and acceleration do not affect motion. Let's check the different components of oscillation using the simple pendulum. Equilibrium position is that position of the body when the forces acting on it have zero resultant. This is actually the position the body takes when it is at rest. Restoring force, as shown in the pendulum, is the force that brings back the body to its equilibrium position, thus it is always directed towards the mean position. Displacement x, or y, is the distance of the body at any instant with reference to the mean position. Amplitude is the maximum displacement of the particle from the mean point. Period is the time it takes for a displaced object to make a complete oscillation back and forth about its mean position. And frequency is the number of oscillations per unit period. The angular frequency, or speed, denoted as omega, is the rate of the particle's angular quantity, given by the formula 2 pi times f, and in radians per second. Simple harmonic motion is a type of periodic motion in which three conditions are observed. First is the force, or acceleration, always acts towards the equilibrium position. Let's explain this using a simple pendulum. So from its rest, if a pendulum is raised to a certain point and released, gravity will act on the particle, giving a component F to restore its place to the equilibrium position. And upon reaching the mean position with the inertia of velocity, the particle will move to the other position until such displacement that the velocity will be zero. And at this state, gravity will act again, creating a restoring force directing the particle to the mean position once more. The procedure repeats on and on. The second condition says that the force or acceleration is proportionate to the displacement. This is explained from the fact that the particle gains force and acceleration from the mean position to its amplitude. Let's say that it starts with 1 kilonewton from the equilibrium position and gains 2 kilonewtons, 3 kilonewtons, 4 kilonewtons, and so on, until it reaches its amplitude. So force is proportionate to displacement. And last condition states that the motion is represented by the harmonic functions of sine theta and cosine theta. Take note that the sine of 0 degrees is equal to sine of 360 degrees and also 720 degrees. And similar with cosine of 90 degrees is also the same as cosine of 540 degrees and 900 degrees. From Hooke's law, we found that the spring's resisting force is equal to the negative of the spring constant by the elongation x. Its total energy is also equated with the summation of kinetic and potential energy. If we expand the equations, we get half of mv squared and half of kx squared. Then considering the extreme particle position, where velocity becomes zero and displacement is taken as its amplitude, we can get total energy is equal to half of m times 0 squared plus half of ka squared, whereby total energy becomes just half of Ka squared. Since we know that energy is constant, total energy can be expressed as half of Ka squared is equal to half of mv squared plus half of kx squared. And note that half can be cancelled out. So, to solve for the instantaneous velocity, we can extract v by root of k all over m times a squared less x squared, where the root of k all over m is also taken as the angular velocity omega. Thus, velocity can be expressed as v is equal to omega root of a squared less x squared. The instantaneous acceleration can be taken from the joint formulas of Newton's second law and Hooke's law, so we arrive at ma is equal to negative k times x. And again, extracting a, we get a is equal to negative kx all over m, where k all over m is considered as the square of the angular velocity omega. So acceleration is taken as a is equal to negative omega squared x. By working with both formulas for angular velocity, which are omega is equal to 2 pi f and omega is equal to root of k all over m, we can also arrive with the formulas for frequency, giving 1 all over 2 pi times the root of k all over m, and period as its reciprocal being 2 pi times root of m all over k. With rotational motion derivation, we can also arrive with displacement formula as a function of time to be x is equal to a cosine omega t, where a from the formula is taken as root of x naught squared plus the quantity v naught all over omega squared. The velocity as a function of time is computed as the derivative of displacement, so it would turn as velocity is equal to dx all over dt, or that would be d of a cosine omega t all over dt, wherein it would turn out as negative omega sine of omega t. And lastly, acceleration as a function of time is taken as the derivative of velocity, or the second derivative of displacement, with which you're going to yield the formula a is equal to dv all over dt, or that would be d of negative omega sine omega t all over dt, turning out to be negative omega squared a cosine omega times t. For the simple pendulum, the resisting force is considered a square from its similarity with the Hooke's law. We can say that k is equal to mg all over L. The angular frequency can be solved as omega, which is initially equal to root of k all over m, and thus can be root of g all over L, where L is the length of string and g is the gravitational acceleration. So plugging this new formula, we can get frequency as f is equal to 1 all over 2 pi times the root of g all over L, and also period to be t is equal to 2 pi times the root of L all over g. Simple pendulum for small displacement are also governed with some conditions. One is the angle of swing or amplitude does not affect the period, which means that the displacement of the particle does not actually affect the time traveled. Second, the mass of a body does not affect the period, which shows that the period of motion is not affected by the mass of the pendulum, but it is directly proportional to the square of its length, as the third condition states, and also inversely proportional to the square of the acceleration, which is listed in the fourth condition. We will talk about waves in Module 8.